Delta IV vehicles are built in the ULA facility in Decatur, Alabama. Final assembly is completed at the launch site by ULA at the Horizontal Integration Facility for launches from SLC-37B pad at Cape Canaveral and from SLC-6 pad at Vandenberg Air Force Base. The Delta IV Heavy is an expendable, heavy-lift launch vehicle, the largest type of the Delta IV family. It is the world's second highest capacity launch vehicle in operation as of now, behind SpaceX's Falcon Heavy. It will come down from second most powerful to fourth most powerful as NASA's SLS and SpaceX Starship come online. It is manufactured by United Launch Alliance and was first launched in 2004. ULA will retire the Delta IV Heavy in 2024. The Delta IV Heavy consists of a central common booster core, with two additional common booster cores, as liquid rocket boosters, instead of the GEM-60, solid rocket motors, used by the Delta IV medium versions. At liftoff, all three cores operate at full thrust, and 44 seconds later, the center core throttles down to 55% to conserve fuel until booster separation. The boosters burn out at 242 seconds after launch and are separated as the core booster throttles back up to full thrust. The core burns out 86 seconds later, and the second stage completes the ascent to orbit. The launch vehicle uses three RS-68 engines, one in the central core, and one in each booster. The Delta IV Heavy can lift around 28,000 kilograms to low Earth orbit, and around 14,000 kilograms to geostationary transfer orbit. It is an all-liquid fueled launch vehicle, consisting of an upper stage, one main booster, and two strap-on boosters. The first launch of the Delta IV Heavy, in 2004, carried a boilerplate payload, also known as mass simulator, and was a partial failure. Cavitation in the liquid oxygen propellant lines caused shutdown of both boosters 8 seconds early, and the core engine 9 seconds early. This resulted in a lower staging velocity, for which the second stage was unable to compensate. The payload was left in a lower than intended orbit. Its first operational payload was the DSP-23 satellite, successfully launched in 2007. It was then used to launch a further 5 visual and electronic reconnaissance satellites for the National Reconnaissance Office through 2013. In December 2014, the Delta IV Heavy was used to launch an uncrewed test flight of the Orion spacecraft, designated Exploration Flight Test 1. On August 12, 2018, the Delta IV Heavy, with an additional Star 48 B5 third stage, was used to launch the Parker Solar Probe into an elliptical heliocentric orbit. The Delta IV Heavy's total mass at launch is approximately 733,000 kilograms, and produce around 952,000 kilograms of thrust to power the rocket skyward at liftoff. The Common Booster Core is an American rocket stage, which is used on the Delta IV rocket. Delta IV rockets, flying in the retired, medium and medium plus configurations, used a single Common Booster Core as their first stage, while Delta IV Heavy uses 3, one as the first stage, and 2 as boosters. The Common Booster Core is 40.8 meters long, has a diameter of 5.1 meters, and is powered by a single RS-68 engine, burning liquid hydrogen and liquid oxygen. Delta IV Heavy, in total uses 3 RS-68 engines. One of the main goals of the RS-68 program was to produce a simple engine that would be cost-effective when used for a single launch. To achieve this, the RS-68 has 80% fewer parts than the multi-launch Space Shuttle main engine. The adverse consequences of this simplicity were a significantly lower thrust-to-weight ratio, and a 10% lower specific impulse, compared to the Space Shuttle main engine. The benefit of this simplicity is the RS-68's reduced construction cost. It is the largest hydrogen-fueled rocket engine ever flown. The RS-68 was developed at Rocketdyne Propulsion and Power, located in Canoga Park, Los Angeles, California, where the Space Shuttle main engine was manufactured. The engine does not use any active cooling, but instead use ablative cooling. This method uses a material on the inner surface of the nozzle, which will vaporize, and then get thrown away, taking the heat with it. The material is thick enough to protect the engine. This is usually made out of carbon composite, which has an extremely high melting point. And this is the reason why the exhaust of Delta IV Heavy is orange, instead of transparent. The exhaust of the engine should be colorless, as it burns hydrogen, which gives water vapor, as seen in the Space Shuttle, but due to ablative material being burned, and mixes with the exhaust, giving it an orange color. The first static test firing of a common booster core was conducted on March 17, 2001, and the final test of the initial program was conducted on 6 May. Testing was conducted using Test Stand B2 of the Stennis Space Center, a facility originally constructed for testing of the first stages of Saturn V rockets during the 1960s. The first launch of a common booster core was the maiden flight of the Delta IV, which was launched from Space Launch Complex 37B at the Cape Canaveral Space Force Station on November 20, 2002. The first flight of the Delta IV Heavy, featuring 3 common booster cores, was conducted on December 21, 2004. On this flight, all 3 common booster cores malfunction, cutting off prematurely due to cavitation in their oxidizer lines, and resulting in the rocket reaching a lower orbit than that which had been planned. In response to the failure, additional pressure valves were installed on future launches. The common booster cores are manufactured in United Launch Alliance's 140,000 square meters manufacturing facility in Decatur, Alabama, and then transported by the RS rocket ship to either Vandenberg Air Force Base or Cape Canaveral Air Force Station, where they are integrated with the spacecraft and other components, such as strap-on boosters and a Delta cryogenic second stage. You might have seen the Delta IV Heavy setting itself on fire just before launch. That's because liquid hydrogen is being released a few seconds before oxygen to protect the engine from the reactive oxygen. The released hydrogen rises up as it is lighter than the atmosphere and catches fire. The Delta cryogenic second stage is a family of cryogenic rocket stages used on the Delta III and Delta IV rockets, and which is also being used on the Space Launch System. The stage is powered by a single Aerojet Rocketdyne and Pratt & Whitney RL-10 B2 engine, which gives a specific impulse of around 462 seconds.